About the sign problem in our previous problem. Actually, there was no sign problem. This expression over here is the correct expression with all the signs. But when you take the low temperature limit, that is very large, x, sine hyperbolic goes to 0 exponentially. X is very large, it diverges exponentially. So 1 over sine hyperbolic squared goes to 0 much faster than 1 over x squared. So at the low temperature limit, that is very large x values, the second term is negligible. I have only the first term, 1 over x squared term, and with a plus sign. And also remember, x is mu b over kt. So there is a mu b over kt, well, this is basically x squared. There's also nk here. So I have x squared multiplied by 1 over x squared, so heat capacity becomes a constant. It doesn't go to 0, as third law of thermodynamics tells us, but that is not a big surprise, considering that we have only done a classical treatment of this system, not a quantum mechanical treatment. Now we will see, we will also do the quantum mechanical treatment, and there we will see that it does go to 0, the heat capacity. Now let's calculate a few more properties of this system. Let's look at the entropy. You see, we know the Z. Well, let me copy Z. This is my Z1, so Zn is just 4 pi sine hyperbolic x over x raised to the power n. X is being equal to beta mu b. Now the entropy might make this concept of negative temperatures a bit more clear. F would be minus kt logarithm of z. This is how we define the free energy. So this will be minus nkt times logarithm of 4 pi sine hyperbolic x over x. Now the free energy of the system will be, the entropy of the system will be the derivative of free energy with respect to temperature. This will be nk logarithm of 4 pi sine hx over x. This is the derivative of the factor multiplying t. And then I have plus nkt times the derivative of the logarithm, which will be derivative with respect to x times the derivative of x with respect to t, which will be mu times b over kt squared, times derivative of that logarithm with respect to x will be cosine hyperbolic x over sine hyperbolic x minus 1 over x. And the energy of this system was this is U. Well, I will not do it explicitly, but in principle, if you solve x from the second equation, substitute it into the first expression, replacing t by energy, S of E, as a function of the energy, well, just directly plotting this function would probably be easier. If you would plot this function, what you would see is when E is equal to minus mu and B, well, all the magnetic moments are aligned with the magnetic field. There is just one configuration that has this energy. So the entropy is 0. When E is equal to plus mu and B, all the magnetic dipole moments are anti-aligned with the external magnetic field. Again, there is just a single configuration, so the entropy is again 0. And somewhere the entropy first increases with energy, and then it decreases with energy. So this is the region of positive temperatures, because remember 1 over T is derivative of entropy with respect to energy. And on the left-hand side of that dashed line, entropy increases with energy. On the right-hand side, that is the T less than 0 region. And in fact, just on the left of dashed line, you have the derivative with respect to energy of entropy is 0, just on the left and also on the right. So if the derivative is 0, that means temperature is infinite. On the left of that dashed line, that is plus infinity, the temperature is plus infinity, right over here. On the right of that dashed line, this is the temperature is minus infinity. You see, the temperature makes a jump, but that's not really a discontinuity because energy just increased by a very small amount. Now let's look at one more concept, the magnetization. What do you remember? Do you remember magnetization from your electromagnetism courses? How did we define the magnetism? Do you remember it? Now, magnetization of a system is the density of magnetic moment. So if you have a system, just you look at a region, you measure the magnetic moment of that region, divide by the volume of that region, that gives you the magnetization of your system. So in our case, magnetization will be, let's say, each magnetic just through the z-axis, this is one dipole, the magnetic moment of one dipole. Let's look at the average. If we multiply it by m, this is the total magnetization of my system. Z is the direction of the magnetic field. The magnetic moment of my system will be in the direction of B. In the Z direction, this is the total magnetization of the system. If I look at per volume, this is the magnetization of the system. Well, this is equal to N over V mu times the average of cosine theta, because mu z is mu times cosine theta. This will be 1 over z n mu over v times cosine theta of e to power beta mu n times cosine theta. Minus beta times the energy of my system is n mu b. Well, sorry. This is z1. Let me remove the n over there. Cosine theta. Okay. Minus beta times E divided by Z, that is the probability. Energy is minus mu B cosine theta of a single dipole. Well, then what I can do is, this is nothing but 1 over Z1 and mu over V, derivative with respect to beta of e to the power beta mu B cosine theta. And let me, if I take the derivative with respect to beta, I get a B, Or let me write the derivative with respect to B. The same thing. Magnetization is usually identified with the derivative with respect to B. If I take the derivative with respect to b, I would get a beta mu cosine theta. I have a mu, cosine theta is already here, mu is here, so I should multiply by kt. This is the magnetization. And let me write this n0, n over v, the number density of these magnetic dipoles, of kt times derivative with respect to beta of logarithm of z1 n0 k, well, remember, logarithm of z1 is minus beta f, so this is minus n0 derivative with respect to b of f. This is how we define the magnetization. Well, if you would like, in fact, df, remember we had the minus s dt minus p dv, and now minus m times, let's say, n dB. This is what my df is. Now I have another degree of freedom, the external magnetic field. If I change the external magnetic field by dB, the change will be given by the magnetization, the total magnetic moment of my system, which is the magnetization times the size of the system. And so you just get this, n over v, let me remove this, 1 over v. Why? Because f is, this is f over n, the free logarithm of z1 is the free energy per particle, not the free energy of my system. Well, we know what Z1 was. This is our Z1. So m being n0 kt, derivative with respect to b of logarithm of 4 pi sine hyperbolic x over x, which will be nkt, derivative with minus, no, not minus, this is beta mu, derivative with respect to x of logarithm of sine hyperbolic x over x, or minus logarithm of x. Well, this is in fact what we had done most of it. N times mu times cosine hyperbolic x divided by sine hyperbolic x minus 1 over x. This is my magnetization of the system. Number density multiplied by the magnetic dipole moment of each one of those magnetic dipoles multiplied by this function. In fact, we already looked at the limits of those functions. So cosine hyperbolic x divided by sine hyperbolic x minus 1 over x goes to 1 for x is very large. This is the low temperature limit. And when x is very small, we had seen that this was 2 over x, right? When x is very small, cosine hyperbolic over sine hyperbolic is this function over here, 1 over x plus x over 2. This is just x over 2. So at large temperatures, that is x much, much less than 1, magnetization is given by n0 mu over 2 times x is, remember that was mu b over kt. This is the magnetization. Do you remember what magnetic susceptibility was? Magnetization is defined as magnetic susceptibility times B. This is called the magnetic susceptibility. So that basically measures how easy it is to magnetize a given system. For a large magnetic susceptibility, even a small b can create a large magnetic moment. But for a system with a small magnetic susceptibility, even a large magnetic moment, magnetic field will not be able to create a significant magnetization. So this chi is defined, this is the definition, derivative of this magnetization with respect to B, evaluate that zero magnetic field. And we see that this is n0 mu squared divided by 2k times 1 over t. You see that the magnetic susceptibility decreases inversely proportional to T at large temperatures. This is called Curie's law. Although this is not a ferromagnet that we are looking at, if you heat a magnet, which is made of a ferromagnetic material, at high enough temperatures, the magnetic susceptibility, the magnetization just disappears. Well, in the case of an actual magnet, that's a phase transition, but this is basically tells us that even for an ordinary magnet, which is ordinary material, if you put it in a magnetic field, it will be magnetized, and the magnetization will just disappear at high temperatures. Questions? So let's look at the quantum mechanical treatment of these systems. Let us look at a more simple case first, a spin 1 over 2 system. G is some constant. This is Q. This is the charge of the system. Q is the charge of the particle. S is the spin. For example, this can be described an electron. If you have a gas of electrons, well, this is the magnetic dipole moment of each electron, ignoring their orbital motion. Here there is no orbital motion. G is some constant. G is 2 for electrons. For fermions, it's a number very close to 2. In fact, Dirac theory of electron predicts G to be exactly equal to 2, but then we have other corrections. It's still close to 2. And this is our Hamiltonian for a single particle. Let me just write this as mu, that's time in the direction times sigma. Sigma will be the Pauli matrices. because for electron S is h power over 2 sigma for the spin of the electron. I will take B in the direction of Z for simplicity, so this will be minus mu times G times B times sigma Z. This is H. And energy levels, my particle basically has two energy levels. This will be minus or plus mu G B. Yes. So there's no G. Well, very similar to my previous case, but without that cosine theta factor. Now my electron, the partition function for the single spin or single electron will be sum over the states, microstates of e to power minus beta E plus or minus. No, sorry. Well, the energy can take two values, so this will be just e to power beta mu B plus e to power minus beta mu B over 2. No, over 2. So twice cosine hyperbolic beta mu B. This is the partition function of one electron.
Exactly what did you do while going from Hamiltonian to energy?
Well, what are the eigenstates of this Hamiltonian?
Okay.
Sigma Z has eigenvalues plus minus 1.
Okay.
So I have the spin of the electron can be only in two states, one with an energy plus mu B, the other one with an energy minus mu B. That's the only thing I did. It's already diagonal. And the microstates, well, there are only two microstates. You see, if you compare it with the classical case, in the classical case, any orientation gave me a microstate. Now I only have two, and nothing else. Free energy minus beta times the free energy will be just logarithm of Z1 to the n, or n times logarithm of Z1. Let's look at the energy. The average energy will be minus the derivative with respect to beta of logarithm of Z1 to the n. The n particle partition function is Z1 to the n. The energy is given by just taking the logarithm of Z1 to the n and derivative with respect to beta, which will be minus n derivative with respect to beta of logarithm of twice cosine hyperbolic beta mu B which will be minus n derivative. That derivative will give me sine hyperbolic beta mu B divided by cosine hyperbolic beta mu B times mu times beta. This is u. Let me again just call beta mu B as my x. Questions?
There should be also two, but
Which two? This two.
in general, yeah.
Well, you see, logarithm of 2 times that cosine hyperbolic is logarithm of 2 plus logarithm of the cosine hyperbolic. If you take the derivative of either, you can think it like that, but if you would like to put the 2's, I have 2 sine hyperbolic divided by 2 cosine hyperbolic. Again, 2's cancel.
Sorry.
Now, at least this time I can determine the temperature as a function of the energy of my system. So U will be minus N. Well, let me also call U over N times mu B as small u. So U, the small u, energy per particle, per dipole, if you like, this will be equal to minus e to the power 2x minus 1 divided by e to the power 2x plus 1. I just multiplied numerator and denominator by e to the power x. So u times e to the power 2x plus 1 is equal to 1 minus e to the power 2x. E to the power 2x times u plus 1 will be equal to 1 minus u. So e to the power 2x is equal to 1 minus u divided by 1 plus u. So 2x is the logarithm of 1 minus u divided by 1 plus u, or x, which was mu b over kt, is equal to 1 over 2 logarithm of, remember this is the definition of u, so if I put it over here, this will be n mu b minus the energy divided by n mu b plus the energy of my system. So this is how the temperature changes with energy. So you see, did I miss a sign somewhere? Probably yes. No, probably no, sorry. So you see, if u is positive, that means the numerator is smaller than the denominator. That fraction within the logarithm is less than 1. If the logarithm of a number less than 1 is negative. So for u, positive, the temperature, if u is positive, the logarithm is a negative number, and hence I have a negative temperature, as we had discussed before. If u is negative, the numerator is larger than the denominator, so that fraction is a number larger than 1, and hence I have a logarithm is positive, and hence I have a positive temperature. So if u is less than 0, n mu b minus u over n mu b plus u is larger than 1, because the numerator is larger than the denominator, and hence t is positive. If u is positive, this is less than 1, and hence we have negative temperatures. So any
U
question?
was the energy of the system, right?
U is the energy of the system. Yes, in fact, in our earlier treatment, we said that as t goes to 0, we had found that u goes to minus n mu b. That is what we expected. That is the minimum energy configuration when all the magnetic dipoles are aligned with the magnetic field. And then we looked at when t goes to infinity, the energy went to 0. So we have negative energies only from minus n mu b to 0 for t larger than 0. Then we said that if we would like to have positive energies, the only way to have positive energy is if we have positive negative temperatures. And like this is, at least for the spin 1/2 case, this is the more explicit demonstration of it. If you look at an n spin 1/2 system, it can have any energy between minus n mu b to plus n mu b. Negative energies will when most of the magnetic dipoles are aligned with the magnetic field, it will have negative energies that they correspond to positive temperature. But if you look at when most of the majority of the magnetic dipoles are anti-aligned with the magnetic field, then we have a positive energy. And if we have a positive energy, that means we have negative temperatures. Let's look at the entropy in this case also. Now the free energy is minus nkt logarithm of z1, which is minus nkt logarithm of twice cosine hyperbolic x. This is the free energy we have. Entropy is the derivative of free energy with respect to temperature minus the derivative of free energy with respect to temperature. Well, I'm not writing it explicitly, but these derivatives are at constant b. I'm not changing b. Well, there is no volume here, the dipoles are not moving around, so I don't need to write it explicitly. So this will be equal to nk logarithm of twice cosine hyperbolic x plus nk times sine hyperbolic x divided by cosine hyperbolic x. This is the entropy of my system. Well, let's see, the U is this one. Now let me take it. This is U. Now what I would like to do is I would like to write this entropy not as a function of, remember, x is beta mu b over kt. I don't want to write s as a function of temperature. I want to write s as a function of u to support my claim that when entropy as a function of energy starts from 0 when energy is minus n mu b, and it goes to 0 when energy is equal to n mu b. That is what I would like to show, if I can. Well, this is u. So s is nk logarithm of twice cosine hyperbolic x minus mu bk mu b u minus u over mu b times k well, cosine hyperbolic x is, remember, it is e to power x plus e to power minus x over 2. Now, I had calculated e to the power x. This is e to the power x. One minus u divided by 1 plus u plus square root of 1 plus u divided by 1 minus u divided by 1 over 2. Well, I can do that product. That will be 1 minus u plus 1 plus u divided by square root of 1 minus u squared, all divided by 2. So these u's will cancel. This is 1 over square root of 1 minus u squared. So S is n times k times logarithm of 2 over square root of 1 minus u squared minus u k over mu b. Well, let's see what happens when, if u goes to plus or minus n mu b. Well, that square root goes to 0. If that square root goes to 0, that fraction goes to infinity. And then I have the logarithm of infinity. Well, there's a problem over here that we need to fix somehow. But at least I kind of obtained what I was looking for. When that square root goes to infinity, well, there should be a minus sign somewhere. Did I miss the minus sign? Let's see. That derivative, this minus cancels this one. I have nk times the logarithm. Then I have nk t over here times sine hyperbolic over cosine hyperbolic. Then I need to take the derivative of x with respect to t, which will be minus mu b over kt squared. Okay, so there's still some more work I have to do over here. It wasn't so trivial, but anyway, if you do the exercise, you should find, where was it? That entropy as a function of u should have this behavior. Well, what you should do, okay, there is this. Okay, I should add this correction here. I had already solved for t. You see, this is the solution for t. I know what x is. Knowing that x or knowing t, I have to substitute it over here in this expression of the entropy, do the simplifications, etc. I will not do that. And you will get this entropy as a function of u. It's just straightforward algebra. So, any questions? So, on Monday you will have a short exam. On Wednesday we will look at the quantum mechanical, the general case. So, this was for s is equal to 1/2. What about mu is equal to some constant times L plus 2s. This is the general relation between magnetic moment and spin and orbital angular momentum. Any questions before we go? Okay, then we don't have the lecture. In the following week, we start on Monday. So next week, you only have the short exam. Well, I mean, the one thing that you should pay attention to is we are more or less doing the same thing over and over and over again. There is a sum which we have the partition function is written as a sum. We have to identify the microstates and find means of evaluating that sum over the microstates. Once we have that, well, the rest is just taking the derivatives and interpreting the results. In fact, the rest of the semester will be more or less along these lines. Identify the summation we need to evaluate, find an approximation to that evaluation. We will look at what happens at short temperatures, at long temperatures, just take the Taylor expansion, and then study a different system. So see you around then. See you in 10 days.